story of a new way to build that uses 80 to 90% less heating and cooling energy. It's called Passivhaus because the buildings are so well insulated and airtight that they don't require an active heating system, like a forced air furnace or a heat pump.
This house is going to cost $100 a year to heat and cool. I think that's a pretty powerful statement.
This technology was invented in North America during the first energy crisis by innovative people who were trying to make significant cuts in energy use.
A famous physicist named William Shockley very early seen that the hugest potential is just in using the energy we have much more efficient.
Today, our problems are much more serious than they were in the 70s and 80s. Climate scientists tell us that we must cut our CO2 emissions 80% by 2050 to help stabilize the planet's climate. And that means drastically cutting our energy use.
There is a deep analysis of the International Energy Agency about the current situation, and they just state that the current energy situation in the world is blatantly unsustainable.
We absolutely need to transform the way we use energy. What happens when you pass that peak and you change the relationship of supply and demand, and you're on the downhill slope?
The fact that we are going to the limits of fracking to get shale oil out of North Dakota and Texas, that we're performing mining operations in Canada to dig out oil sands and process them with natural gas inputs to make a liquid fuel. These are signs that we are really hitting scarcity.
The CO2 emissions that we're personally responsible for don't just go away, that they're actually accumulating. The notion that I was just through casual energy use producing CO2 that will still be there in 25 years and 50 years, that my grandkids will be dealing with the stuff that I just casually put out there.
We will need to know how, by the middle of the century, to reduce carbon emissions by 80 or 90%.
We're able to tell now, I think 2010 was the warmest year on record. If the worst case occurs, then large parts of the planet may be uninhabitable. We may have flooding on the coast. It's going to require an effort that's certainly equivalent to what we would call a wartime effort. And it's going to require the citizenry to accept that this is very important and really see this as a survival question.
And we have to change it quite quickly. In energy relation, quite quickly, that means in the next 20 to 30 years. 20 to 30 years is a short time compared with the development of buildings, compared with the development of power plants. International Energy Agency speaks about an energy revolution, what is needed.
Our housing designs in the U.S. rely on power, electricity, and the burning of fossil fuels. If we did not have easy, uninterrupted access to these fossil fuels, I think a lot of our housing would not serve its main purpose, which is to shelter people.
Almost 50% of our CO2 in the United States is generated from buildings, either from building them, tearing them down, or living in them.
Buildings generate more CO2 than cars, trucks, and airplanes, and once constructed, last many more decades.
The longer it takes us to realize that we have no alternative to making huge improvements in how we build, the less time we will have to do a good job in that transition.
Forget about points, forget about green ratings. How much energy did the building use last year? Let's look at the utility bills. As soon as last year's energy bills for a building become a normal part of a real estate broker's listing, people will have a tremendous financial incentive to make their buildings energy efficient.
There was a very early development of energy efficient architecture in the 70s. In America there was a lot of good examples showing that you can have a better efficiency of, say, a factor 3, a factor 4, and that there is almost no limits on how high the efficiency can be.
First super insulation projects came out of Champaign-Urbana, out of the Small Homes Council. Wayne Schick apparently coined the term super insulation.
These developments ended somewhere in the range of mid of the 80s. It was very difficult to understand that, why these developments stopped.
And that's when, in Germany, Dr. Feist and Professor Bo Adamson, they went ahead and they studied all these concepts. They had studied William Shircliffe, they had studied all the early super insulation books, they had studied Amory Levins's work. They took the whole thing and just really engineered it from top to bottom.
We really proved that this strategy is successful.
In 2007, Katrin Klingenberg built the first prototype passive house in the U.S. in Urbana, Illinois. Kat and builder Mike Kernagis then began the Passive House Institute U.S.
Europe has been setting an incredible example in terms of making subsidies available, understanding that also this new building sector is creating jobs, putting new codes in place that require building construction to comply with Passive House standard. And the European Parliament has put into place an action plan that is working towards making Passive House standard code for the entire European Union by 2015.
Europeans and people living in other developed countries generate less than half the CO2 each year as people in North America. Traditionally, Europeans live in smaller houses, but there is also a growing commitment to renewable energy and the passive house as the building standard.
What is not so well known is that you can reduce it not just by 10% or 20%, but you can reduce it by 80% and 90%. So this is a real solution available.
This building standard is achieved by making the entire building envelope, the walls, floor, and ceiling, thicker than usual, so it can hold more insulation.
So we're using I-joists that are 16 inches deep. So in the 16 inches, we can put in 3 layers of this high-density fiberglass.
Holes where wires, plumbing, and vent pipes enter the building are sealed, and the house is made as airtight as possible. Heat or energy recovery ventilators are used to provide fresh air, transferring heat from the exhaust air to the fresh air entering the building.
We have the air coming in that's cold from outside, and then we have the warm air on this side coming from the house, extracted from the kitchen.
The constant ventilation ensures good indoor air quality. High-performance doors and windows are also installed. Such windows are typically triple-paned and filled with argon or krypton gas.
This is a Passive House certified window. The thermal break in between is really the key to stopping the energy transfer from the exterior to the interior or vice versa.
All material conducts energy, some more slowly than others. For example, metal and brick conduct energy more easily than wood, which is a better conductor than insulation. Thus, a metal window frame, or a solid framing member in a wall, becomes a thermal conductor of heat or cold between the inside of the building and the outside.
In a normal building, this would usually be a thermal bridge where you have a transfer of masonry through the building into another masonry wall. This is a stone is a skin. There's lots and lots of insulation back there. So we've reached this traditional look with extremely modern energy efficiency.
And if you calculate the heat loss... The misconception that the public has that there's going to be one thing that changes the way that we do it. Each area is going to have a small savings, and added all together, it's going to be a very large savings.
The term passive house refers to buildings that are so well insulated and sealed that they no longer need a conventional heating and cooling system. Passive house construction is different than passive solar. Passive solar buildings were designed to collect energy from the sun using large areas of south-facing glass, often causing overheating during the day and cooling off at night. Instead, during the winter, passive house buildings rely on keeping in the heat that is naturally present in a building from the sun, people, TVs, computers, and other appliances. And in the summer, south-facing windows are either shuttered or shaded to eliminate solar heat gain, greatly reducing the need for cooling.
Solar orientation is really important when you are working with the Passive House planning package and trying to achieve a passive house. It shows you on a couple of different spreadsheets how much of your heating demand is going to be met by the sun and how much of it you then have to make up for with mechanical means.
In most climates, all a passive house needs is a small backup heating or air conditioning system, such as a mini-split heat pump, for extremes of hot and cold weather. The Passive House standard requires that buildings use no more than 15 kilowatt hours per square meter of living space per year for heating and cooling. 15 kilowatts is similar to the amount of energy used by a hairdryer or a small space heater. Building very low energy buildings requires the use of energy modeling software.
The heart of the design process with Passive House is using the Passive House Planning Package, or PHPP, that was developed by the Passive House Institute in Germany, that allows you to do energy modeling of the building and also is quite good for optimization and design. The Passive House Institute generates climate data files for specific locations. But it's very nice because it dials it in quite tightly. This is kind of where I do most of my design work. These are the particular envelope measures. These are the inputs, and these are the results coming back from PHPP. So for instance, the air tightness right now is set at 0.6, which is the maximum allowable for a passive house, and my annual heating demand is 12.4. If I change that to 6, which would be typical air leakage for a standard house built in the U.S., it goes up to 49.2. So a major difference just from that air tightness. I think it's a very good verification tool. You put a building in here and it gives you what's been field tested to be a fairly accurate result.
Green building is something that began in the 1990s. There were over 100 different green rating systems around the country. But energy wasn't as important at that time as it is today. If you could get a 10 to 15% improvement, you were happy. Now we're learning today that those green buildings of the past are not too much different than conventional buildings when you have to reach an 80% reduction.
If we take a look at the energy performance of buildings in the U.S., the number 100 represents the current U.S. building code. Existing homes, most of the 113 million houses and apartments in the United States, are at the top of the chart. They typically use 30% more energy than a new home built to code. The EPA's Energy Star standard for a new home, at 85, uses 15% less energy than the average new home. The U.S. Green Building Council's LEED program begins with the same energy goals as Energy Star. Some of its higher ratings use less energy. The Department of Energy's Building America program reduces home energy use by 40 to 50%. At 15, Passive House is the only building standard that cuts energy use by the amount needed to meet CO2 reduction goals. Once this level of energy savings is met, homes with solar panels can more easily achieve a rating of 0.
As we're seeing fossil fuels being depleted, we're going to see energy, costs skyrocketing, and as that happens, people living in passive homes are going to be protected from that. They're going to still have a low energy bill no matter what the units of energy cost.
There are 3 ways to use life cycle analysis on a building. First is to use it to evaluate the energy consumption, secondly the CO2 generation, and third the building costs, both the initial cost and then the operating costs.
And I've seen that Europeans looking at the life cycle of building, how you build a building off-site and on-site and the impact and the waste that it does. Then you get to the point where you're in the house operating it, where passive house then becomes really important. Then there is the demolition of a building and the recycling of a building.
The first step in life cycle analysis is to look at the embodied energy, and that's the energy to construct the building. The second aspect is the recurring embodied energy, because those materials wear out, and have to be replaced. So you have a small amount of recurring energy that's taking place throughout the lifetime of the building. Third is the operating energy that begins the day the occupant moves in, and that operates continuously until the building is no longer being used. And that's principally for heating, cooling, appliances, entertainment, all the plug-in loads that some people call them.
Combined, these represent the total energy use of a building. But if the initial embodied energy is increased during construction to meet the passive house standard, you greatly reduce the operating energy the building will use, and also the total energy used over the life of the building.
Doing life cycle analysis on cost is different than doing it on energy. Passive house and the conventional house will be roughly the same in monthly payments. The mortgage payment will be higher for the passive house, while the utility bills will be lower, and it'll be roughly a wash. But that's for the first 30 years. After that, suddenly there's a huge bonus because you paid off the mortgage, but if you have high utility bills, you don't see much savings. With the passive house, you'll see savings which over the lifetime will add up to tens of thousands of dollars. We're told now by all our governments that we have to reduce our CO2 emissions 80% by 2050. So we need to know the CO2 emissions of a house. And when you look at the CO2 emissions of a passive house, it does actually meet that 80% reduction today.
Over 60 years, the CO2 emissions of a passive house are nearly 1 million pounds less than what is used by a standard home, or even by homes classified as green.
Understanding the building, insulating it well, air sealing it, giving it a good mechanical system, and all these things in new construction can cost the same or less. And then we have the problem of all the existing buildings that need to have the reductions done.
I've wanted to do environmental construction for a long time. We felt that the U.S. Green Building Council LEED program was filling a niche, but we wanted to do something that was really ahead of the curve and was an exemplary project. Passive house really is a cutting-edge energy standard, and if people are concerned about global warming, buildings use, we've heard the numbers before, 40% or whatever it is of the energy use in the country. And so I wanted to try to build an example here in Yellow Springs, Ohio, to show that this is possible, that we can actually make a dent in something like that. And this house is going to cost $100 a year to heat and cool. I think that's a pretty powerful statement.
In about the year 2000, I became aware of Passive House as an approach to design, and I literally stumbled on it using search engines, looking for things like low energy housing, design, passive heating and cooling, and this thing came up that said, what is a passive house? And I clicked on it, and I ended up at the Passive House Institute website and devoured the whole website and thought, this is exactly what I have been aiming to do.
This is the first retrofit in the country to be certified to passive house levels. When we went into it, we just didn't know if it was going to work. The architect and I traveled to Germany, saw what they were doing there, and realized very quickly that America needs to pick up its game on energy efficiency. Over there, they've been dealing with these buildings for 20 years. The nice thing is they've made lots of mistakes, and we can learn from it. One of the concerns people have when they hear about passive house, is it going to look different? Is it going to operate different? And the only things I would say is it'll look the same and operate better.
I designed this house and built this house 12 years ago, and it felt somehow vaguely dishonest to just leave it as a regular old, as Captain Mike would say, a dinosaur house. I want it to last forever and be enjoyed and used as shelter forever.
I'm very energy conscious and been involved in a lot of energy issues. I lived in Minnesota before I moved here. Was involved in many energy activities up there. And so I'm conscious of the concern about peak oil and climate change and being more efficient in our lifestyles, reducing our carbon footprint. So I've decided to retrofit this house to come to close as possible to passive house standards.
One of the nice things with ElectroShield's building is that the 15 to 20% reduction includes an adding of about 1,500 to 1,800 square feet. So we have more square footage, more lighting in that square footage, more heating and air conditioning, and we still have the energy savings.
In 5 or 6 years, we will be able to reduce the energy demand of an existing home by 60 to 80% in each of these retrofits. The most important part of that revolution is increased efficiency. There are a lot of possibilities with very high costs, like building new nuclear plants, but the reduction of the existing energy losses, this is a low-cost concept.
This house is the first house that I attempted to get to Passivhaus standards. We began this project with the goal of building a very sustainable single-family dwelling that would be durable and last for hundreds of years. This was the stated goal of the homeowner.
Because we had lived in all these old, just wonderful, beautiful, character-laden homes that leaked like sieves. And there's nothing wrong with feeling warm in the middle of winter when you live in Minnesota.
But what we tried to use as a major goal was what we call passive survivability, that this house could keep its occupants warm and safe, healthy, and comfortable with a minimum of external energy input other than that which the sun gives us.
We started out knowing we were going to do some sort of energy efficiency. And then along the ways we decided, well, how energy efficient could we go? And got a flavor of Passivhaus and what that concept meant. And does it work in this climate? And so it kind of became a neat science project for us along the way.
The way that we begin to deal with this notion of passive survivability and very, very low energy housing is to, the technical phrase would be to increase the performance of the thermal envelope, and the layman's terms would be add more insulation. And more insulation is typically thicker. So the walls of this house, of the framed portion of the house, are framed with 2 sets of wood stud walls, what we call double stud walls. So on the outside, there's a stud wall. On the inside, right here, there's a stud wall. And in between is an empty cavity. And the whole thing, 14 inches deep, is filled with dense packed cellulose insulation.
We'll have 2 layers of R21 making R42, and then R5 in this 1-inch of styrofoam, which will make a total of R47.
A Passivhaus envelope is super insulated and air sealed. Floor, ceiling, and exterior walls. And high R-value doors and windows are also used.
Triple glazed units, R-value of about 9. The doors tilt and turn.
People can use blown-in fiberglass or cellulose, insulating baths, or foam. The Passivhaus standard does not tell you what to use, just the specification you must meet.
To the extent of the research we've done, we think this is the very first Passivhaus built in Ohio. The walls are 14 inches thick, so the walls are going to be an R60. The floor is R70, and the roof is going to be R100. The insulation in the floor is the same as what will be in the roof, which is a blown-in fiberglass insulation called spider insulation, and it's packed in very tightly at a 1.8 pounds per cubic foot density. The underside of the roof is going to be, in the ceiling side, a layer of OSB, and we're going to make that our air and vapor barrier. These are, of course, south-facing windows, so they have a very high solar heat gain coefficient, meaning they let a lot of infrared heat into the room. When we installed them, we had to be just, of course, incredibly careful with respect to air sealing around the perimeter of them, such that we achieve the rigorous Passivhaus air leakage standard.
Air sealing is labor. And it's odd because, in a way, air sealing, which is one of the most important factors in building an energy-efficient house, we can lose 1/3 or more of the heat from a house simply through air leakage. You can have the best windows, you can have the best insulation. If the envelope, if the exterior shell of the building is leaky and either losing air and letting cold air in, your efforts are semi-useless.
Here's a wall that was built about 25 years ago, and it illustrates some of the problems that we weren't aware of at that time. The hole was drilled about 1 inch in diameter, and a single wire is run through it. There's no caulking, there's nothing really to stop cold air moving down from the attic or warm air that might be in the stud cavity moving upward. You see that we've actually used caulking to seal both the outer wall and the inner wall. And we've used foam where foam was appropriate to fill any potential voids. This kind of attention to detail can make a tremendous amount of difference in the actual performance of this building.
180 CFM.
We now test all of our houses with a blower door test at least once. Often we do it twice before the sheetrock is put on so that we can identify major areas of air leakage and actually fix them before the sheetrock is applied. And then after the sheetrock is applied and essentially everything is sealed up so that we can finish and determine that it was indeed tight enough. The electric grid was turned off and this house had no power. If it was the dead of winter, if the sun was shining, this house would stay warm enough to be comfortable without a conventional heating system, without electricity.
It's the only building standard that's actually testing people on air tightness. And you see incredible gains with air tightness. When I started with Passivhaus, most of the builders around here told me that it couldn't be done. The thing is we did it. The first day that we had this house blower door tested, I was incredibly nervous. And it turned out to be a non-event. There's no way we're going to meet the energy goals that we have without upping our game in the U.S. construction market as far as air tightness.
The best idea to do the very best you can, and that's not 15% reduction in energy savings, it's a 80 or 90% reduction in energy saving, and that is possible.
When we build very tight houses, in order to maintain indoor air quality and keep our occupants healthy and the house healthy, we need to provide what's called whole house mechanical ventilation. That means we control the fresh air coming in and we control exhausting the stale air going out, and we balance that. And what that means is we've simply calculated the amount of fresh air needed in a continuous flow to keep the occupants healthy, and we bring in that much air and exhaust out that much air at the same time to keep the house in balance.
When you have a modern house in which you've made the walls and ceilings so tight, you, of course, make the air stale just by living inside the house. There are also some materials that are sometimes used in a house or brought into a house. A lot of the furniture that's made today is made with a form of chipboard where the glue of that chipboard does what they call outgas, and it puts some pollutants into the air. Carpeting can do the same thing. So because any of these things exist, and because we use up the air in a house, we need to be sure that the right amount of air is there. They say about 10 cubic feet a minute per person is a good standard.
That air then, the fresh air then goes through the ducts to primarily the bedrooms and the living spaces. And then the yellow ducts, the return air is brought out of the bathrooms, kitchen, moist areas, and returned and gone out. So it's an entire house system to move fresh air through the house from the living spaces and bedrooms to the bathrooms, kitchen, and out.
Why are you taking it out?
Because everyone likes to see it.
Oh.
This is the magic device?
Yeah, that's a heat recovery core.
This is a heat recovery ventilator. What you've got is your supply air would come in on this side. It passes down into here, and this piece here is a heat recovery core. And the fresh air, the cold air in the wintertime would pass in this way. On the backside from this duct, the air from the bathrooms and kitchen, it passes through in another direction. This core here is made of layers that the air doesn't mix. It passes through these multiple layers in opposite directions. And what happens is warm air coming in one side and cold air going the other. They pass through on either side of these membranes and transfer that heat from one to the other. So by the time the air comes in, over 90% of that heat difference is transferred.
We will not have the same effect that you would have with a forced air furnace. Temperature differentials very quickly, like from cold to high. We will not have any drafts, we will not have any noise, we will not have any dust in a passive house, because everything is such low flow, so steady. Temperature in a passive house stays completely steady.
People think because we don't have a furnace that it's going to be, we're going to be freezing through the winter time, and it's a lot more comfortable than a normal standard house. You don't have the drafts coming through, and I never have to even think about wearing slippers because the floors are always warm.
There's over 113 million households in the United States, and even ones built yesterday and not even sold yet already are obsolete in terms of not integrating the principles, the techniques that will allow that house to function, be relevant, and be a resource in the future.
We have one retrofit project that is very exciting, and what is so special about this retrofit project? This home is only 11 years old. I like to point out his quotes right here that were in one of the newspaper articles recently. We're going to try to make this thing tight enough to float in the ocean.
Tad and I have both been worried about global warming since 2000. One day he said, "Would you mind if I went to Urbana 3 times this summer?" And so at first it was just to become a certified passive house consultant. Like all journeys, you don't know what you're getting to. And then when he came home last December, so another Christmas, and said, "I'm going to do our house," what I finally started to say is, well, somebody has to go first.
This house at 2,100 square feet, it's just slightly smaller than the national average. Many millions of houses have been built in the 70s and 80s and 90s with relatively modern energy codes. So our house had double glazed vinyl frame windows. We had 6 inches of insulation in 2x6 walls. So that's all fairly conventional, and we basically added to that.
In deep energy retrofitting, walls are either thickened to the outside or to the inside to hold more insulation. Tad Everhart used Larsen trusses to thicken the walls of his home. The truss is attached to the existing building on the outside.
This wall used to end right here, and now it comes out another 10 inches. And that insulation is 100% high density cellulose that was blown in from the top. So these Larsen trusses go all the way from the mud sill to the top plate of the second floor. These are the workhorse windows of the house because these bring in a great amount of heat on clear days. Those windows don't open anymore, but to make up for it, we've got our operable windows on the west side of the house and the east side of the house. So in the summer, when we want to go with natural ventilation, we can open those windows and we can get a nice flow-through ventilation from the west to the east.
Got a moment to answer a question?
What we've noticed already is the house is more comfortable, and it's very stable, so we don't have these big temperature swings. We constantly have fresh air coming into the house, and we love that. It's wonderful to go up and put your hand on the register and know that instead of just old air that's gone through the furnace and come back for another cycle through the house, it actually was outside 30 seconds ago. You've recovered the heat from the stale exhaust air, put it into the fresh incoming air, and you're breathing air just as if you were outside.
Heat your house with a hairdryer!
I purchased this house in August of last year. The house is 560 square foot living space. My cousin, who is a building contractor, he has built the walls out, which is allowed for the expansion of the walls 9 inches, which now allows us to put in 2 R15 fiberglass insulation, which is R30, plus a 2-inch foam board, which is another R10. This is added onto the insulation that was in the basic house of blown-in cellulose, which estimate about R10. So our estimate is that the final wall insulation will be roughly R50. The insulation that we've added to the floor of the house from the crawl space is R40. There was originally between the attic joists cellulose insulation.
Right.
We blew on top of that another 20 inches
Okay.
of blown-in cellulose. There's 7 windows in the house. If we placed all of them with triple glazed windows, we took out one door, was not a well-insulated door, and there was a lot of cold coming through that door. When I purchased this house, it had an electric forced air heat, and it was using extreme amount of electricity, and I just felt this wasn't consistent with the way I wanted to live. We have removed the air conditioning, taken that electric furnace out, and we are currently installing a heat air exchange system that will bring air in and exchange the heat and moisture with the air that is exhausted from the exchanger.
We're going to have a fresher house than the one across the street, because we're going to make it a point to move the air out, even though some old houses may move 10 times an hour air turnover inside and out because of leaking and bad windows and doors. We're going to establish our own, and we're not going to lose the heat when we exchange it.
Although Ward's home no longer needs a furnace, he uses a small mini-split heat pump for heating and cooling.
It will only be necessary under the most cold, extreme conditions.
Ward's whole house retrofit resulted in an 80% reduction in heating energy use.
There's lots of technical issues around energy, but when we start talking about size, we're looking at the social aspects, the cultural aspects of energy.
Newly built houses, they tend to have much higher amount of square footage per person, and they also tend to use far more electricity than their older counterparts.
From 1950 to 2010, the average house size in the United States more than doubled. During the same period, the average number of people per home declined. The result is that the average square foot per person has increased more than 3 times, from about 300 to about 950.
The greatest potential we have in America is for people to reevaluate what they need and make decisions regarding how many additional people might be able to live in their house, or could they live in a smaller part of their house. The potential for co-housing on an existing neighborhood basis. The power of community as an incredible resource to compensate for lack of money and lack of resources that you might be able to invest in an individual house.
Nancy Darren and 2 other women have chosen to reduce their energy consumption and CO2 emissions by sharing living space.
Nancy Darren is a woman who's been involved in energy and social actions a good part of her life. And she decided she moved towards retirement rather than just remain in her big house. And she recruited other women who were nearing retirement and living in large homes to downsize. They have 3 apartments in separate areas, bedrooms, living rooms, but they share the common facilities such as laundry and kitchen.
We decided to remodel a house that we could each have a different area. Between the 3 of us, we reduced our footprint by 1,500 square feet. If I give up a little bit of what I'm used to in my habits of having a whole house to myself, I can share expenses and share responsibilities to where there's more time to just sit and visit or to be engaged in my community.
One of the problems that happens to retrofitting is that there's the ultimate of what we would really like to do on each house, and then there's what we can afford to do.
So we have to be realistic and stage these things with a sense of this long-term urgency of making very, very deep reductions and not just 5 and 10% reductions.
One of the projects I think is really pretty innovative, located in the Bay Area of California. What they chose to do is create a comfort zone within the kitchen and basically renovate the kitchen walls, let the rest of the house float in terms of temperature. There's still sleep in the rest of the house. They couldn't have afforded to address the entire exterior skin of their house. And that gives them deep reductions without as much deep debt.
Without heat, the temperature in the warm room floats between 60 and 65 degrees. They only heat the rest of the house on a few special occasions.
If we embrace the fact we've got to transform how we use energy, there are a variety of ways to figure out how to get there.
If you look only at energy, then we can go on a few more decades until the energy runs out. But when you look at CO2, we cannot afford to burn the energy that's in the ground. So it's gone from a matter of convenience to a matter of survival.
To build a new power plant, it costs 5 times more than to retrofit houses to Passivhaus standard. It's what Emery Labin said in the 80s.
If you're willing to really cut your energy consumption, then all solutions become much easier and much more possible. If you actually achieve a 90% reduction from standard construction in your house, and then you want to use renewables of solar or wind, it takes a lot less. So if the first concentration is on energy reduction, then whatever solution you have to do through technology is smaller. If you aim for a 90% reduction of energy use and you get to 80%, we're a lot better off than if you don't try for it at all.
I really like this, you know, I mean, some people get excited about looking at their fancy car. I get excited about looking at this energy data and how little energy I'm using the way I live comfortably.
But I think it's a beautiful, profound thing to have a building that's really serving you with such a tiny, tiny amount of energy. And I hope that people can really get a grip on how good that would be for them, and obviously how good it would be for the other issues that we're encountering in this world: war, peak oil, pollution, global warming. It, in one fell swoop, helps with all of those problems.
It's a development of a kind of liberation, because now you can build your energy future. You do not depend on the oil, you do not depend on the nuclear energy. You just depend on your own knowledge and your own work, and we have seen that that is possible.
I really believe that saved energy is the invisible oil that is in existence everywhere, and everybody can access it. Nobody has to buy it from anybody. Just smart building techniques will access that wealth, the wealth of conserved energy, and anybody can get it.